All right, thank you for this coming to our second seminar. Actually, I've emailed the professors the list for the semester, so you may want to ask your advisor if you haven't heard, because your name may be on there, and it could be next week. So every slot's filled. If you didn't get a chance, you can talk to me, and we can put you on the schedule as a backup. We don't have as many slots as students. This week, Leng is going to present to us. Of course, everyone here knows Zen because he's been here for several years, not forever. He's worked with Professor El-Kadi on his PhD. Now he's a postdoctoral researcher here at the Illinois Center for Transportation. He came from Southeast University in China. And what year did you come?
2005.
2005. So been here some times. I know he's worked on a variety of topics, including GPR and now warm mix asphalt, and he'll be talking about his warm mix project. I believe this is the tollway project?
Yes.
Yes. Okay. Thank you.
Yep. Okay. Thank you, Professor Reeser, for the nice introduction. Good afternoon, everyone. Thank you all for coming to today's payment seminar. And in this presentation, I'm going to talk about the short-term performance of plant mix warm mix asphalt, which is a part of a research project we have recently completed for the Illinois Tollway. And before start, first I'd like to acknowledge my co-author, as well as the PI of this research project, Professor El-Kadi. And in this presentation, I will mainly go through the following topics. First, I'll provide a little introduction.
No, louder. You speak louder.
Okay, sure. Yep. First, I will provide a little introduction to the background of this study, and then the research objective and scope will be presented. And after that, I will talk about the testing material and the experimental program, and then the results of the laboratory testing and the on-site modular testing will be presented. And after that, I will discuss the traffic opening time for warm mix overlays, and in the end, I will conclude this presentation with a summary. So as we all know that the warm mix asphalt is a sustainable pavement material whose use in the United States has increased very rapidly in recent years. And compared to the traditional hot mix asphalt, the warm mix asphalt can be produced at a much lower temperature, therefore leading to several environmental benefits, such as lower energy consumption, less greenhouse gas emission, and a decreased worker exposure to asphalt fumes. However, due to different warm mix preparation techniques, the physical and chemical properties of the mixture can be altered, which can result in different short-term and long-term mechanical behavior of the mixture. And in the literature, many research studies have been conducted to investigate the long-term performance of the warm mix asphalt, while the research on the short-term performance of the warm mix asphalt is relatively limited. So in this study, our main research objective is to determine the short-term performance of the warm mix asphalt using both laboratory performance testing and field modulus measurement. And in order to achieve this objective, we have conducted the following research tasks. So first, the early age mechanical properties of a warm mix asphalt was evaluated with respect to a control hot mix asphalt through comprehensive laboratory performance testing. And then the effect of curing time on the short-term performance of the warm mix asphalt was evaluated by conducting the lab testing at different curing periods. And here, the curing time refers to the time after the mixture compaction. And finally, the appropriate traffic opening time for the warm mix overlays was determined based on the field modulus measurement. So in this study, in order to produce the warm mix asphalt, a commonly used chemical additive, Ewson 3G, was added to a selected control asphalt mixture. And the control asphalt mixture is a typical SMA mixture that has been widely used in large-scale expressway overlay projects in Chicago area by the Illinois Tollway. And as this table shows, the control SMA has a nominal maximum aggregate size of ½ inch. It uses a PG64-22 asphalt binder with 12% of ground tile rubber. And it also contains 8% of fine portion of the fractionated wrap. And the compaction temperature for the control SMA is 305 degree F. And the Ewson SMA had the exactly same mixture design as the control SMA, except that 0.5% of Ewson additive was added to the asphalt binder. And the compaction temperature of the Ewson SMA was 45 degrees lower than that of the control SMA. And this table shows the matrix for the laboratory performance testing. And as we can see, in this study, 4 laboratory performance tests were conducted, including the dynamic modulus, Hamburg wheel track, indirect tension, and semicircular bending. And in order to evaluate the curing time effect on the mixture performance, each of these tests has been conducted at different curing periods, as shown in this table. And the dynamic modulus test was conducted at room temperature, which is 77 degree F, and at 6 different loading frequencies from 25 Hertz to 0.1 Hertz. And the Hamburg wheel track test was conducted at 86 degree F under dry condition with a maximum loading cycle of 20,000. The indirect tension test was conducted at the room temperature with a loading rate of ½ inch per minute, and the SCB test was conducted at 10 degree F with the CMOD control rate of 0.028 inch per minute. So here I want to mention that in order to eliminate the reheating effect on the mixture's performance, all the testing specimens tested in this study were compacted in the SO plant right after the SO mixtures were produced. And the specimen preparation in this study was conducted in the following steps. So first, the fresh plant-produced mixtures were collected from the truck, and then these mixtures were splitted and then compacted using gyratory compactors in the SO plant. And after that, these gyratory specimens were protected using PVC tubes and then transported from the SO plant to our lab at Acher. And because the distance from the SO plant and our lab is around 150 miles, the specimens to be tested at 3-hour curing time were transported using a chartered airplane to ensure we have enough time to cut core and condition the specimen before the testing. And the specimens to be tested at all other curing times were transported using trucks. And finally, all the specimens were cut and cored in our lab before they were tested at designed curing times. And in addition to the laboratory performance testing, the on-site modular testing was also conducted in this study using a lightweight deflectometer, which is also known as LWD. And the basic principle for the LWD testing is based on measuring surface diffraction induced by a dropping weight. And this equation shows how we can calculate the surface modulus based on the LWD measurement. And in this equation, E0 is the surface diffraction modulus, and F is the factor for stress distribution, which equals to 2 for flexible pavement, and mu is the Poisson's ratio, normally 0.35 for SO mixture. Sigma 0 is the applied stress under the plate, and A is the radius of the loading plate, and D0 is the measured diffraction at the center of the loading plate. And the construction site for the LWD testing was located on Interstate Highway 355 in Chicago area. And in this construction site, both the control SMA and Iverson SMA were used as the overlay mix on top of a PCC pavement. And the LW testing was started right after the final compaction pass till up to 24 hours. And in each overlay section, the LW testing was conducted at 3 locations, one on the left wheel pass, one on the right wheel pass, and one between the 2 wheel pass. So next, I'm going to share with you some of the results we have obtained from the laboratory testing. These 2 figures present the dynamic modular test results at 25 Hertz and 0.1 Hertz at the room temperature. And as we can see, at both frequencies, the dynamic modulus of both mixtures increased with the curing time. However, at the same curing time, no significant difference was observed between the 2 mixtures, as supported by these overlapped arrow bars. And these arrow bars represent the average dynamic modulus plus and minus 1 standard deviation. So when the arrow bars of 2 measurements are overlapped with each other, we consider these 2 measurements are not statistically different. And these 2 figures present the rotting depths measured at 5,000 loading cycles and 20,000 loading cycles in the Hamburg wheel track test. And from these 2 figures, we cannot see any clear trend between the curing time and the rotting depth, which indicates the curing time is not a significant factor affecting the rotting performance of the warm mix asphalt. And when we compare the rotting depths at the same curing time, we found that the rotting performance of the two mixtures are comparable to each other in most cases, except that at the 72-hour curing time, the rotting depth of the Iverson SMA is higher than that of the control SMA. The tensile strengths of the two mixtures were measured through the IDT test in this study. And as this figure shows, in general, the control SMA provided higher or equal tensile strength compared to the Iverson SMA, with only one exception, which is the 12-hour curing time. And for the Iverson SMA, which is the blue columns, the tensile strength increased within the first 12 hours and then stayed relatively constant. And for the control SMA, which is these red columns, the tensile strength increased after 24 hours and then stayed relatively constant. And the fracture resistance of the two mixtures were characterized through the SCB test in this study. And as this figure shows, the curing time does not significantly affect the fracture resistance of the two mixtures. Although the average work of fracture for the control SMA decreased with the curing time, this decreasing trend is actually not statistically significant, as supported by these overlapped error bars at different curing times. And at the same curing time, we found that the fracture resistance of the two mixtures are in general comparable to each other, as supported by all these overlapped error bars at different curing times. And after talking about the lab performance testing results, next I'm going to introduce the on-site LW testing results. And for the on-site LW testing, it is very important to measure the surface temperature of the pavement, because the asphalt material is a viscoelastic material, and its modulus is sensitively affected by the temperature. So this figure shows the measured surface temperature within 3 hours after the pavement compaction. And as we can see, right after the final compaction pass, the surface temperature of the control SMA was around 140 degree F, and the surface temperature of the Iverson SMA was around 120 degree F. And the cooling rates for both mixtures are very close to each other within 3 hours after compaction. And this figure plots the relation between the measured surface modulus and the surface temperature for both mixtures. And as we can see, there is a clear negative relation between the surface modulus and the surface temperature for both mixtures. However, at the same surface temperature, we found that the Iverson SMA actually provided a lower surface modulus compared to the control SMA. And for the wall mix overlay constructions, one of the challenges is to determine the appropriate traffic opening time. And in this study, we proposed a method to determine the traffic opening time for the wall mix overlays based on the LWD testing results. And the criteria we used in this study is that the control SMA and Iverson SMA should provide the same modulus, but not the temperature at the traffic opening time. For example, let's assume the control SMA can be open to traffic at the surface temperature of 120 degree F. Then based on the relationship between the surface modulus and the surface temperature, we can find that at the traffic opening time, the surface modulus of the control SMA should be 206 KSI. And in order to achieve the same surface modulus for the Iverson SMA, the Iverson SMA should be open to traffic at the temperature of 110, which is lower than that of the control SMA. And then, based on the relationship between the surface temperature and the time after compaction, we can determine that for the control SMA, it can be open to traffic 1.4 hours after compaction. And for the Iverson SMA, it can be open to traffic half hour after compaction, which is much earlier than the control SMA. And then by following the same procedure, we also calculated the traffic opening times for both the control SMA and the Iverson SMA when the traffic opening temperature for the control SMA is 140 degree F and 100 degree F. And based on the results showing in this table, you can see that although the Iverson SMA has a lower modulus compared to the control SMA at the same temperature, it can still be open to traffic earlier than the control SMA due to the lower compaction temperature. So finally, I'm going to summarize the findings which we have encountered in this study. So in this study, we found that the curing time effect is in general insignificant on the writing potential, tensile strength, and fracture resistance of the Evison SMA. And we also observed the dynamic modulus of the Evison SMA increased with the curing time. However, since a similar trend was also observed in the control SMA, this curing effect is not considered to be caused by the Evison additive. And at the same curing stage, we found the early age dynamic modulus and the fracture resistance of the Evison SMA are comparable to those of the control SMA. And before 72 hours, the Evison SMA and the control SMA showed similar writing resistance and tensile strength, but after 72 hours, the Evison SMA showed slightly lower writing resistance and tensile strength. And finally, the LWD testing results indicate that the on-site modulus of the Evison SMA was lower than that of the control SMA at the same temperature. However, due to a lower compaction temperature, the pavement sections constructed with the Evison SMA could still be open to traffic earlier than those sections constructed with the control SMA. So this research is sponsored by the Illinois Tollway Authority, and we'd like to acknowledge the valuable input from Mr. Steve Gillen of the Illinois Tollway. And we also want to thank all the research staff and graduate students in our lab who have helped with the lab testing and the field measurement. So with that, I'm concluding my presentation, and thank you all for your attention.
Okay, is there any questions for Zen?
Yeah, Zen, did you get a chance to compare the LWD modulus with the laboratory measured dynamic modulus or something? I mean, order of magnitude differences, something in the similar order of magnitude, or are we not comparing apples to apples here or something? What's your comment on that?
Yeah, actually, based on the results I have presented in this presentation, you can see, based on the laboratory dynamic modulus testing results, it seems the Evison SMA and the control SMA had a similar dynamic modulus at the same curing stage. But in the field, we did find that the Evison SMA actually provided a little lower modulus than the control SMA. So there is a little difference between the laboratory dynamic modulus test results and the field LWD modulus results. So I think this is reasonable because these two tests, they are based on completely different kind of a mechanism. And the testing condition, one is the sinusoidal loading, one is the impact loading. So I think it's reasonable to get some difference between these two tests.
I have a question to follow up. Why did you select the Boussinesq solution for the back calculation of the surface modulus? Because that would seem like you would actually introduce a fairly large error in your modulus prediction because of the compressibility of the layer. In fact, I would guess, without doing the calculations, that your modulus is much higher than you're actually predicting.
Yeah, that's true. I think that's just a simple way for the back calculation, and it's a method commonly used for back calculating the modulus based on the LWD testing results.
But it makes sense if you have a thick granular layer, but when you have elastic layer over almost a rigid plate, your errors are going to be quite large using just a single layer solution.
Yeah, I agree that that's just a simple way for the back calculation. Yeah. There could be some error introduced by using that method.
And I guess they would come closer because I thought your laboratory results were higher. So your field results are probably under predicting what actually should be. At least that's what I'm thinking based on what I recall.
Yeah, here's the lab results. Actually, lab results show that they are pretty close to each other.
I'm saying the dynamic modulus is higher than the field. the field modulus. So that would
Okay.
explain why your field modulus is small, because you're using the wrong equation, or using an equation that introduces a lot of error in the actual modulus prediction.
Yeah, actually, the field modulus is not the modulus of the asphalt mixture itself. It's a kind of a surface modulus. It combines the effect of all the different
Layers.
material layers. Yes.
Yeah,
so
of course.
probably we cannot directly compare the values.
Actually, in the LWD, there were two more sensors, offset sensors.
Yep.
You probably didn't use those.
No, we
I
only
mean,
did a
again,
single
had you
point.
used those, you could have maybe done some
That's true, yeah.
individual layer back calculation for the moduli, which might have corrected some of that stiff underlying layer issue.
Yeah,
But
yeah,
again, if
yeah,
you
I
just
agree.
use the center deflection exactly, then you're pretty much with the LWD user's guide, you're limited to using that one equation.
Right, right. Yeah, when we use the LWD in that way, we actually assume all the underlying layers for the two sections are the same.
Right.
They are same, but probably in the field, they're more or less there's still some difference there. But we assume they have the exact same kind of payment structure. But yeah, definitely, if we have more data points, we can back calculate the modulus for each layer instead of just relying on one single point. Yep.
Right. I'm going to go back to Deb's question. I think you will be comparing apples to oranges. I don't think that we should be comparing the dynamic modulus to the stiffness that you are measuring, because the way in which you are loading the materials is completely different, and that will give you different results. Then you go back to the questions, then why you are doing the lightweight deflectometer. There was one reason for doing this, which is trying to monitor. We were debating to do the deflection or to back calculate this simplified equation to get the modulus. And we know that if you are having a thickness like this, around 2 inches, also you are getting more errors because of this equation too. But we were more interested in seeing the increase that you are getting in the modulus, or call it stiffness, whatever, or the reduction in the deformation as you are having a decrease in temperature. And that will allow us to come to a point to say, now is this road is open to, or is this road is ready to open to traffic. The alternative technique, which is usually used right now, is they open the traffic based on temperature. So in that case, what we are trying to say is you cannot open the traffic based on temperature, because you are already supposed to open the traffic when you finish compaction for the warm mix, and that's not true. So that's what we're trying to show here. No, for the warm mix, because usually in the hot mix you open the road at 140 degree.
120
So
or
if you
40.
look here, by the time 0 or 130, it depends who you talk to. So by the time 0, you are already getting at 140, 130. So in that case, is the material stable? And the answer is no. So you need to look for something else in order
Some
to
mechanical
decide
property instead of the
open
temperature.
traffic. Yes.
More questions? No questions. Stan, why don't you ask about whether we can use it on airports, huh?
No, my question is about the seasonal effect of this. Looking at cure time, paving late fall, it freezes, say 2 or 3 hours, gets below freezing 2 or 3 hours after placement. What's going to happen to the mix?
Sorry, can you just
If you're
elaborate?
paving late in the fall,
Yes.
let's say at 4 o'clock in the evening when they
Right.
quit.
The
it's-
opening time will be different.
Right.
Yes.
But what happens if you're showing your graphs there up to 24 hours and the stiffness? What happens? It's 36 degrees when you quit at 4 o'clock in the evening, and 3 hours later you're below
Yeah.
freezing.
Yeah, yeah, that's a very good point. Actually, here in this presentation, I'm just showing an example how we use this method. And here we show the relation between the surface temperature and the time after compaction. These are from the kind of a real field measurement. But under other weather conditions, we don't have all the data, but we have some other tools to use. There's a software available called the MultiCool. It can predict how the pavement surface temperature change with time after compaction under different weather condition.
What would be? I think maybe his question was different
Okay,
than that. His
sorry.
question is, I think, how does the warm mix perform in a condition where it rapidly freezes relative to hot mix?
More or less. I just want to know what the seasonal effect of like the season paving would be on it.
Yep. Thanks.
Stan, that's not intended to go ahead and pave using warm mix during a freezing season. I mean, it will extend the paving season a little bit, but not to the point that we're going to be doing it during the freezing time. Usually, what you do with hot mix asphalt, it depends, I guess. Like, for example, I'll pick like in Wisconsin. They do it usually at 40 and increasing. When they get into below 40 degree, then they will not pave. After 2 or 3 hours, you will find that here, both for the warm mix and the regular hot mix, they will start to have some stable temperature. It's interesting, in another study, we found that even for the hot mix asphalt, you take the measurements after a week, and you're going to find that it's completely different than if you take the measurements after 2 hours. Actually, it's part of another study where we took all these specimens and we stored them for a month, and we did the study again on them, and the modulus was double, literally double. So I do believe that hot mix asphalt do cure, not just the warm mix, and their properties change with time even if you don't expose it to aging.
So eventually you'll develop some sort of seasonal limitations on when it can be put.
Absolutely. I mean, this will push the season, the paving season, a little bit, but that doesn't mean that you're going to be paving during a freezing point, unless somebody going to be using some admixtures or whatever. We have not looked into that.
Sorry, I got another question now.
Yep.
What was? Do you think this will be a different result if it's not SMA? Because it would seem that SMA, since you have stone-to-stone contact, the effect of the binder is going to be reduced potentially. And my second question is then on airports with higher contact stresses, would you have to modify this time after compaction? No, I'm asking him.
Yeah, I think, all the results we obtained here should not be simply extended to all different types of mixtures, because now, we are testing SMA, and especially for probably the rutting performance, the SMA is very good at the rutting, so probably we cannot see much difference there. And if it's a different type of mixture, probably we will see some larger difference between the warm mix and the hot mix. But I think if we are trying to predict the performance of other type of mixture, the best way is to run the test on those mixtures, but not just based on base results on the SMA mixture. And the reason why we are interested in SMA is because the Illinois Tollway, they use a lot of SMA in the Illinois Tollway, and they are interested in to introduce this mixture into their SMA paving. So we selected this mixture, specific mixture, for our testing. But I think for other mixtures, the best way to predict their performance is to run tests on them, not just simply based on these results. And
I can also help you on this. It's if you look at the testing that we did for the let's assume that we are doing testing on SMA and hot mix asphalt, and you run a dynamic modulus. In many cases, when you are doing a testing in compression, you will find that the hot mix asphalt, dense hot mix asphalt, may perform better even than the SMA. Even if you run Resium modulus, it is usually giving you a higher value, but that doesn't mean that the hot mix asphalt is better than the SMA. It performs better in the field because it has more durability, If you run it in tensile, it will give you a higher tensile. If you run a fracture energy, it will give you a higher fracture energy. So the test sometimes that we are running is not an indication, like the dynamic modulus, in my opinion, it's not an indication of the performance of the materials. Now we're trying to look into a different way of the testing, which is the pull-push, because the asphalt concrete, it's usually fail in tension, not in compression. So measuring the compression to compare things is definitely not the right approach. So far, from the people who looked into other materials, the warm mix is performing the same almost as the hot mix asphalt. So would I use it in the airport? Absolutely. I mean, there is some concern of trying to use it, because if you have a failure in an airport, it's usually more noticeable than if you have a failure in a highway. But would I have the guts to do it? Absolutely. I wouldn't have a problem with that based on the short-term performance that we have.
Yeah, and I think Brian tested some other mixtures. Probably.
Yeah, Brian, you did the regular hot mix asphalt too, right?
Yeah, probably. You can share some of your testing results.
Pretty short till you guys come up here.
I think for the most part, you'd see that you'd exacerbate the differences. I think specifically with rutting resistance, you'd see a huge difference. We saw that. And then, I mean, having 15% GTR in the binder, I mean, that makes a difference too if you're using a 6422 like I used in our study. So I think those two things have a huge effect upon the results that you would have. But I mean, we got similar results, but like I said, they were the differences were exacerbated quite a bit.
Because of the PG64.
Yeah, and I mean, I think if you have a dense grade mix compared to an SMA, I mean, what was the binder content that you had?
It's a 6.2.
Yeah, I mean, we were around like 6.7. I mean, that was really high, but it was a surface mix too. It was 9.5 millimeters, so.
And also you need to add the foaming, the process of the warm mix
True.
also has an impact.
True.
Right, yeah.
Yeah.
It's a bigger,
Okay, any last questions? Okay, let's thank Zen for his presentation.
I have to thank Zen because he jumped into this topic after Matt left when he got sick. So thank you for picking up on this topic and just keep it going.